Hello students, welcome again. How are you all? Doing good now? That's very fine. So as you can see, numericals written on the board. So it's time to have few numericals based on the concepts that we have learned so far. So let's move on. I'm just reading question number 1. A test charge Q is moved without acceleration from A to C along the path from A to B and then from B to C in electric field E as shown in figure that I will be drawing on the board. First, calculate the potential difference between A and C, and second, at which point of the two is the electric potential more and why. So I'm just drawing the diagram for the first question so that we can have better idea. So here actually the electric field is given to be uniform, and in this uniform electric field E, the test charge is kept at point A, which is having coordinates 6, 0 given in the question, and it is shifted to finally point C, where actually the coordinates are given to be 2 and 0. So it is brought here from A point via B. So there is a B point given right here. So B point has got coordinates 2, 3. So first A test charge is brought from A to B, and then it is brought from B to finally C. So this is the question, students, given. Now for the first part of the question, we need to calculate potential difference between A and C. As we all know, the electrostatic field is conservative in nature, so it doesn't depend on the path followed. So finally, it only depends on the initial and final position. So the test charge is brought from A to C. Whether it is via from A to B and then from B to C, we can directly consider the test charge being brought from A to C, as the work done is independent of the path followed between initial and final position. So for the first part solution, we can have VC directly minus VA, potential difference between C and A, which is equals to minus integral from A to C of vector E dot dl. This is very basic definition of potential difference. Minus integral from A to C E dl cos. Now try to identify the angle between E electric field and displacement vector. Displacement is being brought from A to C opposite of E. So here angle would be 180. So this is cos 180 is minus 1. So this minus 1 and this minus becomes plus. So here we have A to C EDL. Now students, as can be seen, electric field is uniform throughout this length, displacement dl. So it can be taken out. So it is E integral from A to C dl. So when you integrate dl, you will get L. And what is the L? 6 minus 2, that's 4. So here you will be getting 4E as the first answer. Fine with this? Okay, let's move on to the second part of this question. Second part of the question says at which point of the two is the electric potential more and why. So between A and C, you need to tell which point will have more potential and for what reason. So here, as we all know, that electric potential is always along the decreasing electric field. So the decreasing electric field is this one. This is the so electric potential direction is along the decreasing electric field. So here the potential will be more and here it will be small. So you will be writing VC is greater than VA. So this is, and how will you write the reason for this? You will be writing as we know the direction of electric field E is along decreasing electric potential V. As from the definition you can just see. Okay, so this is the solution of first question. Let's have the second question now. So here actually we can have the second question solution with us. Okay, so just let's have second question. Find the electric potential at the surface of a gold nucleus given radius of nucleus to be 6.6 into 10 powers to minus 15 meter and atomic number of gold is 79. So we'll be using here actually a very basic definition. So electric potential is 1 upon 4 pi epsilon naught charge upon distance from the source charge. So here this has got 9 into 10 powers to 9 value, and we have here atomic number of gold given to be 79. Q equals to Ne we are using. So this is number of electrons as equal to atomic number into charge on electron 1.6 into 10 powers to minus 19 upon how much is the radius. Radius is given to be 6.6 into 10 powers to minus 15 meter. So students, when you just solve it, you'll be getting 1.7 into 10 powers to 7 volt as your answer. Okay, let's move on. So let's have next question number 3. The electric field at a point due to a point charge is 20 Newton per coulomb and the electric potential at that point is 10 Joule per coulomb. Calculate the distance of the point from the charge and the magnitude of the charge. You need to calculate distance as well as the magnitude of charge. So for the third question, actually electric field is given to be 20 Newton per coulomb, and what else is given? It's electric potential perhaps given. Yes, it is 10 Joule per coulomb, and then we need to calculate magnitude of charge as well as distance. So we directly write down what the expression for the electric field intensity at a point and thereby potential. It's 1 upon 4 pi epsilon naught charge upon distance square. So this is actually equation number 1, let me call it, and the electric potential is 1 upon 4 pi epsilon naught, it's charge upon distance, equation number 2. So just do one thing, you just divide this equation by this. So dividing second by first, we have, what do we have? Actually V upon E, we have this will get cancelled, Q will get cancelled, and we have simply R with us. So directly we can have values here, it's 10 upon that 20. So this perhaps will give you 0.5 meter as your answer. Now just place this value of R in equation number 2 so that you can have magnitude of charge. Now using equation number 2, we have electric potential is given to be 10, which is equals to this value has got 9 into 10 powers to 9. Electric charge we need to calculate, and this is 0.5 we just have calculated. So the value of Q with us is now equal to 10 into 0.5 upon 9 into 10 past to 9. So this is simply 5.56 into 10 past to minus 10 coulomb. So this will be your answer for this question number 3. So let's move on for the question number 4. Question number 4 is 2 point charges 4 microcoulomb and minus 2 microcoulomb are separated by a distance of 1 meter in air. At what point on the line joining the charges is the electric potential 0? So two charges are given at certain distance and we need to calculate at what point in between them we have 0 potential. So here I'm just drawing the diagram so that we can have better understanding of the question. Here actually 4 microcoulomb charge is given and here it is given minus 2 microcoulomb charge, and let we have a point N here where due to the presence of these two charges the electric potential comes out to be 0. So we will be writing potential due to this charge at this point, and later on we will be writing electric potential due to this minus 2 microcoulomb charge at this point, and by applying principle of superposition we can have total potential at point N, and that should be equated with 0. So here actually the separation between these two is given to be 1 meter, and let we have the distance of this end point from this 4 microcoulomb charge is x. So obviously this distance would be equal to how much? It will be 1 minus x. Okay, so let's move on. The potential at N is given to be 1 upon 4 pi epsilon naught into charge upon Q1, I must write, upon, this is distance is x, and then plus charge second upon distance is 1 minus x. So this has to be equal to 0. Okay, let's move on. Just place the values. This will be 0, and here the charge is given to be 4 into 10 past to minus 6 upon x minus second charge minus 2 micro, 2 into 10 past to minus 6 upon it's 1 minus x. So this is just equal to 0. Now as can be seen, 10 past minus 6 can be taken as common, and just on simplifying it you will be having 4 by x which is equals to 2 by 1 minus x, and 2 to the 4. So this is simply x upon 2, just reversing, inverting both the sides, 1 minus x, and this is this will give you x equals to 2 by 3, just cross multiplying. So 2 minus 2x, that comes here 3x which is equal to 2, and 2 by 3 is equal to this, and this will give you 667 meter as your answer. Okay, so let's move on. Okay students, so let's have next question. Question number 5th. So it's calculate the potential at point P due to the charge configuration shown in figure that will be drawn on the board. If small r is very much greater than A, then show how will you modify the result. So let's proceed. Question number 5th. So the diagram given here is actually, this is the test point P, and here we are given assembly of charges. Actually here it is minus q charge given, and here it is plus q charge given, and here it is again plus q charge is given. So the distance from this mid charge plus q of this P point is given to be r, and these are at AA distances. This is A and this is another A. This is another small A distance. Okay students, so this is the question given. How will we be proceeding? We have to calculate the potential at point P due to this assembly of charge. So we will be calculating the potential due to this minus Q charge here at P. Later on due to this plus Q charge potential at P. And finally potential due to this plus Q charge at P. Now by applying principle of superposition, total potential will be the sum of these three potentials. So this way we can calculate the total potential. Okay, so let's proceed. The potential at P, V equals to V due to minus Q charge plus V due to plus Q charge plus V due to again plus Q charge. So this is actually simply the principle of superposition application. Okay, now just place the values. 1 upon 4 pi epsilon naught will be common in all. So here actually it is, see, it's due to this charge is minus Q upon, what's the distance of this test point from this? It is R plus A. So I am writing it R plus A plus, due to this plus Q charge, what's the distance? It's R. So charge upon distance plus, again due to this it's plus Q charge, and then distance would be total R minus A. So this will be the distance, the Q upon R minus A. Okay students, so just have the simplification of this. 1 upon 4 pi epsilon naught, and you'll be having here inside it's Q by R plus 2QA upon R square minus A square. So actually this is, when you just solve it, having the LCM as R square minus A square, and later on just cross multiplying this to this and this to this. So on simplification you get this. Now with condition moving ahead, if say R is very much greater than A, then we can neglect this A square and retain R square here. So then R square minus A square is nearly equal to R square itself. Therefore the modification of potential expression would be 1 upon 4 pi epsilon naught charge upon distance, this one, plus 2QA upon, here you will have R square. So this would be your final answer, I must say. Actually this expression will be getting as the final outcome for this question. Here A square will be neglected and R square will only be there, and numerator will remain as it is. First term will have no change at all. So this is the final outcome. Okay, so we can have now next question with us. Question number 6, I must say. Calculate the potential at a point on the axis of a ring of charge of radius small a, given charge on the ring equal to Q and the distance of the observation point from the center of the ring is small x. Okay, fine. So let me just have the diagram first so that we can have better understanding of the question. Suppose here we have a ring. Say this is a ring, and on the ring, actually ring is of radius given in the question. Its radius is given to be A, and from the radius the charge on the ring is Q. So we'll be considering a small element of this one, which will have dq charge, and the distance of the test point P of the center of the ring is small x. So the line joining or the distance of this element from this point is say small. What should we write? Say let me call it to be small r. Okay, just call it small r. So we'll be writing the electric potential due to this small element of the ring at point P. Later on, integrating that, we can have total potential. Okay, so you just start the electric potential at P due to small element dV equals to 1 upon 4 pi epsilon naught charge dq upon distance small r. Fine with this? Now the total potential V equals to integral 1 upon 4 pi epsilon naught will be a common term. So integral it's dq upon small r. So actually this distance would also be constant. So when we integrate this, we'll be having q. Okay, and this r would be simply under root a square plus x square. So just proceed now. 1 upon 4 pi epsilon naught into q upon under root a square plus x square. So this is actually the final solution. Okay students, let's have next question. Charges 2 into 10 power to minus 6 coulomb and 1 into 10 power to minus 6 coulomb are placed at corners A and B of a square of side 5 cm as shown in figure. How much work will be done against the electric field in moving a charge of 1 into 10 power to minus 6 coulomb from C to D? Test charge is also given. So let me just draw the diagram so that we have better understanding. This is a square, and here actually let me call these 2 points to be A, B, and this to be charge say Q1, which is given in the question, magnitude Q2, and this let me complete the square first. So this is point C, this is point D, and the side is given to be 5 centimeter. So this is 5 centimeter, 0.05 meter you can call it. Okay, so actually we will be writing the potential at D due to this and this, and potential at C due to this and this, and later on the total potential at C and total potential at D will be subtracted so that we can have the work done. Fine. Okay. So now we write the potential at C, let me call it VC, which is equals to, now see, this has got distance 1 upon 4 pi epsilon naught will be a common term, and here the charge is Q1 and distance is AC plus charge is Q2 upon distance is BC. So just now placing the values, we have this as 9 to 10 power to 9, and magnitude of first charge is given to be 2 into 10 power to minus 6 upon AC. Students will be getting under root 2 into 0.05 plus second magnitude of charge is given to be 1 into 10 power to minus 6 upon distance would be 0.05. So students, when you just solve it, you will be getting 9 into 10 power to 3 into 2 plus root 2 upon root 2.05 into root 2. So this would be actually the solution of this. And now just calculate potential at D. So VD would be equals to 1 upon 4 pi epsilon naught charge Q1 upon distance AD plus charge Q2 upon distance BD. Okay, now just place the values 9 into 10 past to 9 into first charge magnitude 2 into 10 past to minus 6 upon distance AD would be 0.05 plus second charge 1 into 10 past to minus 6 upon, it will be under root 2 into 0.05. Okay, so students, when you just solve it, you'll be getting approximately this 9 into 10 past to 3 again, here inside 2 root 2 plus 1 upon the LCM would remain 0.05 under root 2. So actually this much will be the potential at D due to this A and P. Now to calculate the work done, we need to calculate potential difference between C and D. So W would be equals to Q into VD minus VC. So Q is given to be 1 into 10 past to minus 6 discharge into this would be a common term that also you may write 10 past to 3, and here inside you will be having VD is 2 root 2 plus 1 upon 0.05 under root 2 and minus this thing minus actually this you may take as LCM minus 2 minus root 2. So students, when you just solve it, you'll be getting 0.053 joule. Okay, so students, this is the final answer of the question that question is demanding from us. So that's the end of today's session. So students, do like and subscribe the channel.